we're going to take a look at the properties of the elements in relation to their position in the periodic table. And what we're going to see is that there are two trends that occur with these properties. The one that we'll address in this video are the primary trends based on just the number of electrons that are in the outer shell and the nucleus. So if we take, for instance, silicon and germanium, two elements that are in the same family on the periodic table, silicon being one row higher up than germanium. And in looking at the size, the relative size of these, we might imagine that, the germanium being lower down the periodic table, there are more protons, more electrons, so we would imagine that that's a larger atom. So what we want to do, though, is just kind of verify that. So if we look at silicon, silicon we find has 14 protons in the nucleus, and we're just going to show the shell. So silicon is in the third principal energy level. So there's going to be two levels that are completely filled with electrons. And then the third level will have 4 electrons in it. And then if we look at germanium right below it, germanium is going to have 32 protons in the nucleus, and it's going to have 3 shells that are completely filled. And then in the 4th shell, it will have 4 electrons in it, similar to silicon. So we have an S2P2. For the primary trends, we're not going to distinguish between the S's and the P's. I'm going to go ahead and label each of the principal energy levels. So that would be 1, 2, and 3, and 1, 2, 3, and 4. Okay, so we see the number of principal energy levels. So it's pretty obvious from here that the germanium is going to have more principal energy levels. So the N of the valence shell for the germanium is larger than the principal energy level for the valence shell for silicon. Okay. So from that perspective, it seems like that would be, the germanium would be the largest. But there's one other factor that we need to consider. We need to consider how strongly those electrons are being pulled toward the nucleus. So in the case of germanium, we have 32 electrons that are pulling those, or 32 protons that are pulling those electrons in. Whereas in silicon, we only have 14 protons pulling those electrons in. What we want to look at here is something called the effective nuclear charge. And the effective nuclear charge is going to be the pull that the valence electrons, the outer electrons, feel toward the nucleus. So if I take a look at one of the valence electrons in silicon, okay, so I'm going to pretend I'm that electron. If I look in toward the nucleus, I'm going to see 14 protons pulling on me to try and keep me in. But that's not all I'm going to see. I'm also going to see the 2 full valence shells of electrons that are negative, and they're going to be tending to push me away. The effect is that those are going to be shielding some of that positive charge. And basically, it's a 1-to-1, in this primary trend, it's a 1-to-1 shielding. So if we count the number of electrons there, we have 10 negative charges that are shielding 10 of those 14 positive charges. So we would have an effective nuclear charge then of 4+. So each of those valence electrons in silicon is being pulled in with an effective nuclear charge of 4+. If we go down to germanium and we do the same thing, and we look in toward the nucleus, and there are 32 protons pulling the that one electron in. And if we add up all the electrons that are inside of the valence shell, we should get 28. And so for the germanium, we're going to have an effective nuclear charge also of 4 plus. So we see then that the effective nuclear charge on the valence shell for silicon is equal to the effective nuclear charge on the germanium. So our answer, our judgment in terms of which one of these would be larger, is going to be based on the number of principal energy levels, since the effective nuclear charge on both of these would be the same. So, but it's important that you address both of those. Okay, so here's our what we need to make sure we do when we compare to. First is that we comment on the number of principal energy levels, right? So that's the n value. And second, that we comment on the effective nuclear charge that's pulling on those outer or valence electrons, pulling them toward the nucleus. All right, here we're going to take a look at two elements that are right next to each other. So we'll continue with silicon. So we've already got our 14 electrons in the or protons in the nucleus, first shell, second shell filled, and then 4 electrons in the third principal energy level. Phosphorus is in the same period, so it's just 1 over, so there are 15 protons there. Again, the first shell is filled, second shell is filled, and the third shell now will have 5 electrons in it instead of the 4 that silicon has. So n equals 1, 2, 3, n equals 1, 2, and 3. So at first glance, we might be tempted to think, all right, well, we have more protons, more electrons. The phosphorus is going to be the larger atom. But let's take a look and just go through our logic. Remember, the two things that we need to comment on are, 1, the number of principal energy levels, and 2, the effective nuclear charge on the valence shell electrons. So let's go ahead and do that. So obviously, the n for the valence shell on silicon is equal to the n for the valence shell on phosphorus. So there's number 1 that I've taken care of. All right, what about number 2? Well, let's take a look at the electrons on the silicon. We just did the silicon on the last problem, so we know that the effective nuclear charge that electron feels is a 4 plus. There's a 4 plus, net 4 plus pulling it in. If we look over at the phosphorus, that same electron there, we're going to see 15 protons pulling it in, and we see 10 electrons shielding, partially shielding 10 of those 15 protons. So our effective nuclear charge for the phosphorus is actually a 5 plus. So now if we go down here, then we should record that in our reasoning. So reason number 2, we've got that the effective nuclear charge for silicon is less than the effective nuclear charge for the phosphorus. What this is going to do then is that those valence electrons in the phosphorus are all going to be pulled in a little bit closer. So they're in the same principal energy level, but because there's a greater effective nuclear charge, those electrons are going to be pulled in a little bit closer. The second term we'll look at is an ionization energy. Now, ionization energy is defined as the energy required to remove the most loosely held electron. It can be represented by this equation here. If we take our same silicon element and we'll go to germanium. So silicon, we have again our, we'll draw our structures. So we have our diagrams to explain or help us explain the relationship here. We have our effective nuclear charge, 4 plus for the silicon, 4 plus for the germanium, and our principal energy levels. And of course, we go back to, the principal energy level for silicon is less than the principal energy level for the germanium, but their effective nuclear charges are the same. So the charge that's pulling on those outer electrons from the nucleus is the same. So you would expect, oh, well, maybe these would have the same ionization energy, the same energy it requires to remove the electron. However, if we take a look at the principal energy levels, we notice that the electrons that we're trying to remove from germanium are farther away from the nucleus. So what effect is that going to have? Well, if they're farther away from the nucleus, it's kind of like if you held magnets together. If you held two magnets really close together, there's going to be a really strong attraction. If you hold the magnets farther apart, there's a much weaker attraction. So the electrons that are farther away from the nucleus are going to be easier to remove as long as they have the same effective nuclear charge. So in that case, then the germanium would have the lower ionization energy. So our conclusion here would be the ionization energy for silicon would be greater than the ionization energy for the germanium. It's electrostatics, the plus-minus attraction and repulsion, and looking at the distance and the number of principal energy levels. So hopefully you'll get a chance to do some practice problems with these and kind of work with the ideas and make sure that you formulate some strong connections in your mind with how to do this.